I'm going to call it example 1, support vector machine classification. All right. Now I need to open up, we're going to do this on the iris data set. So to do that, I need to go back to, I think, decision trees. Actually, I think I need to go back to regression-based classification, and I'm going to pull in loading the iris data set from that. Hit F5. Okay. So I have my iris data set. It loads and it runs. So let's say build and train the SVM classifier. So first we want to build handles for the model of the linear SVM classifier. So we're going to go scalar is equal to sk.preprocessing.standard scalar. The scaling is very important. We'll run that to make sure it loads up. And we'll go support vector machine underscore CLF for classifier is equal to sk.svm.linear support vector SVC. And we're going to set C is equal to, I have it to about 1 million. A nice capital C. A nice big C to give us a nice wide margin with lots of flexibility. All right. So now I want to build a pipeline to contain all of my models. Or a model element. And that's just so I can call the pipeline each time instead of calling them individually, because I need to scale things. So scaled support vector machine CLF is equal to sk dot pipeline and then open up a list. In that first spot of the list, I'm going to create a tuple and going to say scalar linear SVC SVM underscore CLF. I'm going to hit F5. Oh, sklearn has no attribute pipeline. So let's come up here and say from sklearn import pipeline. All right, so something's not right in this code. Just break it out like this so I can maybe find it. Module object is not callable. Oh, I need a. Yeah, that's not confusing at all. Dot pipeline. And the second one has a capital P. So it's sk dot lowercase pipeline dot capital pipeline. Okay, thank you. Now it's as easy, right, as just train my model. So scaled underscore svm underscore clf dot fit capital X comma y lowercase y capital X y. Nope, that's going to be a capital Y. All right, and now let's go ahead and let's see if we can plot it. So we're going to go plt.figure. How do I want to do this one? Okay, so I actually have a number of plots up above. So I've created this plot. I'm really only concerned with my petal length and my petal width again. So we're going to take this right-hand plot. And I'm going to copy all of that down. I'm going to hit F5 again. And now I get a nice plot here. All right. So we can plot, what we want to do is plot our decision boundaries into this. And there's no super great way to do this. So using some of our understanding of the map, we are going to build out our lines. So we're going to say B, which is our bias term, is equal to support vector machine underscore CLF dot decision, decision function. And then I need to feed it a list of negative scalar dot mean underscore divided by scalar dot scale, and that should give me back my bias terms. But it doesn't because I have a mismatch, because I only want my two features but that's not what I trained it on. I trained it on all four features, but we don't want to plot all four features. I will update the code later, but let's do something. Let's do something on clean here. All right, I'm debating just starting again and typing it exactly as I have it, instead of trying to redo things on the fly. You want to do that? I think that's going to be best. Okay, so I will update these notes. because I changed terminology. Example _1 B. That's fine. Here's what we're going to do. You can keep some of that, or you can just type along, whatever you want. But I only took 2 of my data points, so I'm just going to take 2 of my data points. All right, so let's just do that. Okay, we want to load our data. Iris is equal to datasets dot load _ iris. Depends how you imported it, but sk dot, that's how I should import it. Yeah. So load iris. To be honest, the way I code is not the way I code in class in front of people. But when you code in class in front of people, I think it's better to spell more things out than less. I'm going to go capital X is equal to iris and square brackets data. And I'm going to go, I just want some of the data for just the 2 classifiers that I'm interested in, right? So for just two sets for 2 features. So I'm going to skip the first 50 because they're all Certosa. I know what they are. They're super easy to classify. So 50 colon, comma, a tuple for 2, 3. It's going to get me my petal length, my petal width. And then Y is equal to iris going to feed that target from 50 to the end, which is equal to 2, and that'll be a true state or a positive state for iris virginsea. All right, now I've got that loaded. I'm going to go ahead and plot it. plt.figure, plt.plot x for y is equal to 0, 0, comma, x for y is equal to 0, comma 1, comma. I like to have them as squares because that's what they were before. And I like to have color equal to CC1 just because that's what they were before. Otherwise, it's going to be blue and yellow instead of yellow and green. And I just don't want it to change. I'm going to go label is equal to versicolor. Hit F5. All right, I should get just some of my flower points now, but that's what I like. I'm going to copy this down, and I'm going to call this y is equal to my true states for x, y is equal to 1 for x, 0, 1. Going to make it a diamond. Going to make it color number 2, which makes it green. And going to make it virginsea. These are my positive states. Now I'm going to go plt.xlabel. Petal length in centimeters. And then my plt.y label is petal width. And then, of course, I want a plt.legend in plt.type layout. All right, so that gives me a nice model of just those 2. So now, instead of training the support vector machine on all 4 classes, I'm just going to train it on these 2 classes. Does that make sense?
plt.ylabel. So
Oh, yeah, thank you. All right, so now I can go ahead and train my support vector machine. So you can copy up that code from before, or I'm just going to retype it. So build the handles to regularize data. Build the handles for the model. Scalar is equal to sk.preprocessing.standard scalar. That's it. And support vector machine underscore CLF classifier is equal to sk.support vector machine linear support vector machine classifier. I'm going to go C is equal to 1,000,000. All right, so build the pipeline. And that's going to be scaled underscore support vector machine underscore CLF equal to sk dot pipeline dot capital pipeline. And then I'm just going to break that down onto a next line. Now I need a tuple, which has scalar and scalar. And now I need a tuple that has linear support vector machine, SVC, comma, SVM underscore CLF. And I don't think I need another comma, so I should be able to run that.
SVC.
Support vector.
Where you define the SVM classifier, you used SVC the first time, but later SVC.
Oh, so here?
Yeah.
SVM.linear SVC. Thank you.
Why is it C?
Support vector classifier. So we're within support vector machines, and you have linear support vector classifier. You can also have linear support vector regression, and then nonlinear. Okay, now we can train our model. So scaled SVM underscore CLF dot fit capital X lowercase y, and that should train our model. All right, now we want to, again, I'm plotting this. So we want to build and plot the decision boundary. First, we need to convert the on-scaled parameters as SVM is solved in the scaled space. All right, so we have to on-scale our parameters because we don't want to plot it in the scaled space. We want to plot it in the on-scaled space. So we're going to go B, which is our bias terms, is equal to support vector machine underscore classifier CLF decision function, open and close our brackets, parentheses, and then our brackets, negative scalar dot mean underscore will give us a value divided by scalar dot scale underscore. That should work out well. And then W is equal to SVM underscore CLF dot COEF underscore 0, because it's going to give me a few and I just want the first one, divided by scalar dot scale underscore. So that'll give me my weights and biases. I'm going to actually put the W up top because we say weights and biases, so that would be helpful. Okay, so the decision boundary, if we look at our weights and biases, is W0 times X0 plus W1 times X1 plus our bias is equal to 0. That is our decision boundary. It is a mathematical definition of our decision boundary. So from that, we can show that X1 equals W0 divided by W1 times X0 minus B divided by W1. Just kind of moving some classifications around. Now, if we were to do that, we first need to build out a W0. W0 is equal to NP dot linspace of 4, 5.9. I'm going to go 5.9. You could probably just go, let's just go 4, 6. That won't matter. Famous last words. F5. And that will build out a space for us to plot against. And now my decision boundary is equal to negative W of 0 divided by W of 1 times, now I've defined all of my X naught, so I can go X naught minus my bias term divided by W of 1. This is a X0. All right, we have made it somewhere. Let's go ahead, and I'm just going to go ahead and go plt.plot X0 comma decision underscore boundary comma, I'm going to say, just make it a solid black line. And there is a decision boundary that's probably not in the right place. Okay, what did we... I hope that's not where my decision boundary is. X naught equals a linspace from 4 to 6, 200, negative W0 divided by W1 times X0 minus B over W1. That one looks fine. So W is equal to SVM classifier coefficient 0 divided by scalar dot scale underscore, and B is equal to SVM decision function negative scalar underscore mean divided by scalar dot scale. No. Okay.
Yeah.
Mine, I think works.
Oh, does yours work? Are you getting a classifier that looks through your middle?
It's a little off, but yes.
Maybe I just need to run it again. Oh, look. It has some real randomness to it. How about that classifier? How's that one? Okay, convergence. Lib linear failed to converge. Increase the number of iterations. Always read your warnings. Okay.
Yeah, I ran it again, and this one's off.
Yeah. So I need to run it for more convergences, but for right now, that's fine, right? So we all understand that sometimes you got to train more to get a good model. All right. So that's my classifier. Now I want to plot my margins. I need to get my margin. So my margin is 1, but I have to do it out of my weight space because my weight space is scaled. So I'm going to come up here and go margin. Actually, I'll do it up here, but margin is equal to 1 divided by W of 1. And curbs underscore up is equal to decision underscore boundary plus margin. And curbs down is equal to decision boundary minus our margin. For some reason, it's taking a long time, which is a little unnerving, but that's fine. So we're going to go plt dot plot. It's still going to be x0, but now it's going to be curbs up. And I'm going to call it K, make it a black dashed line. And then curbs down. I'm going to stop that. I don't know why it's crashing. There we go. And that is a support vector machine with very wide boundaries. And I have very wide boundaries because I set my C factor to be very high. So if I lower my C factor, I should get narrower boundaries. There we go. And as you can see, this is definitely a soft margin because it's allowing fluctuations. It's using quadratic programming to solve the math problem that we laid out. So it will allow some things to be misclassified because it's not hard boundaries.